Why is Faraday's law fundamental to electrical engineering? Have you ever wondered how electricity is generated or how devices like motors and transformers work? The answer lies in a principle known as Faraday's law. This law is essential to electrical engineering because it explains how a changing magnetic field can create an electromotive force, often referred to as voltage, in a conductor. At the heart of Faraday's law is the idea that when the magnetic flux through a circuit changes, an electromotive force is induced. Magnetic flux is essentially the amount of magnetic field lines passing through a specific area, like a coil of wire. When this flux changes, whether due to the movement of the conductor, variations in the magnetic field strength, or adjustments in the coil's orientation or area, an electromotive force is generated. The relationship can be expressed mathematically as electromotive force equals negative the number of turns in the coil multiplied by the change in magnetic flux divided by the change in time. The negative sign indicates that the induced electromotive force opposes the change in flux, a concept known as Lenz's law. This principle is vital for conserving energy in electrical systems. From the perspective of electrical engineering, Faraday's law is fundamental because it governs electromagnetic induction. This process is key to converting electrical energy into mechanical energy and vice versa. For instance, in transformers, Faraday's law explains how an alternating current in one coil can induce a voltage in another coil. This allows for efficient power transmission by stepping up or stepping down voltage levels. In electric generators, mechanical motion alters the magnetic flux through coils, which induces an electromotive force and generates electric power. Electric motors utilize this law by describing how current-carrying conductors in magnetic fields experience forces that create motion. Inductors also apply this principle to store energy in magnetic fields when the current changes, influencing circuit behavior. Understanding Faraday's law is crucial for electrical engineers as it allows them to design and optimize various devices and systems. It also forms the foundation for studying electromagnetic fields and waves, which are essential for communication technologies, sensing applications, and power electronics. In essence, Faraday's law connects magnetic fields with electric circuits, enabling the generation, transformation, and control of electrical energy across numerous engineering applications. This principle is not just theoretical. It is a practical tool that shapes the way we harness and utilize electricity in our daily lives.